So for this lesson, we are going to cover 8.1, and we're going to start to look at a hypothesis test. So we've been doing confidence intervals. So we're looking at that sample of our population, and we're like, well, how confident are we that everybody's around this mean? That's our one of our point estimates, or around this percent that or proportion, this many out of this many. So those were like our middle, and then we had an error kind of out, and we could say, all right, based on the sample, the population is around between these two numbers. So this is similar. It shows a similar thing, but it's a little bit different. And so we call it hypothesis testing. And what we really want to focus on is kind of the idea of it is an 8.1, and basically how to set it up. And then for 8.2 and 8.3, we'll actually solve them. So a hypothesis test is a procedure for testing a claim about a population. So we're going to test a claim. So if somebody says the average height of a male is 5'10", we're going to test that claim. Is that true? We would then gather a good sample, right? And we using our sampling methods and quite a few people, and we would test that claim. Okay. And we never say like, no, they were wrong. We're right. Males are now 5'11" or 5'9", whatever. And so we could go, any direction like that. We never say like it's for sure. We say we have evidence in favor or against. So we have evidence for something. We don't say we for sure have it, right? So that is the idea of a hypothesis test. So on here, I have a little example here of a claim. 3% of all Americans have died or will die from the coronavirus. So that 3% number was out for a while during COVID. Another example would be the population mean weight is known to be 157 pounds, but we think it has gone up. So that claim could include like what people are thinking, but it typically has either a percent or so many out of so many, which is a percent, right? If you divide it, or it would be a mean. Okay. We could also do a standard deviation, which isn't hard. Literally, we're not doing it for time. I've got to it one time in stats, so we probably won't cover that part. You do cover it a little bit in biology. It doesn't really matter. You just follow the formula for whatever point you're looking at, whatever middle of your data or whatever you're looking at. Okay, so I'm saying we will learn methods to okay. So then we're going to get to this hypothesis. So we have something called our null and our alternative hypothesis. And the null is denoted with this HO or sometimes in HA, right? HO, H1, HA. I don't even see the HO one. Oops. Yeah. I was saying HA. That's because I'm pointing at the wrong one. I was like, what? Where's the HO? So this is how your book denotes it. The alternative is the A. I was like, it's not an A. Okay, so we usually just use this symbol, and the null is always equal to your claim. Okay, I don't really care if you're going for the claim or against the claim, but it's always equal with your null. It doesn't matter. Everyone thinks the null should be like what your claim says. It's not. It's always equal. Null is always equal. Equal. So highlight this little equal, and you will get half of this homework right. Just remembering it's equal. Then our alternative is whatever you're claiming, whatever you're looking at. So it could be not equal if it's two-tailed, both directions. So we could have not equal. So our null is always equal to our claim. So if we're just looking at like 3% of Americans died from COVID, then our null would be P, it's a proportion, equals that 3%, 0.03. Our alternative would either be not equal if we just say, we don't think it's 3%. We don't know if it's lower or higher. We just don't think it's 3%. We can test that. And in Wyoming, we've tested it during COVID. We tested it against the CDC's information and stuff in Wyoming was always lower. Okay. Whereas some places where they were concentrated, lots more people, like New York, it was actually higher deaths. Okay. So COVID talk, COVID schmovid, just kidding. It's really crappy when you get it. So then we have less than or greater than, and that's going to bring in our tails. Or we're saying we're greater or we're saying less than. I'm moving my hands my direction, which is opposite for you. So I will just show pictures of that in just a second. I have them, don't I? Where are they? Ta-da. So I'm going to scroll down, then we'll go back up. So this is kind of what a two-tailed test looks like in our null, or in our normal looking bell shape here. So we're testing both sides, okay? And then we could be doing a less than, so we're testing this section over here, and we could be doing a greater than. So when we look at the null and we look at the alternative, we're either going to reject the null or we're going to accept the null, right? So that's the wording we use. So we always go to that null. So that's why it's talking about rejection region, okay? And it'll become that p-value. What's the probability of being in the rejection region? So we'll look at this p-value as well. Okay, so I'm going to scroll back up. So let's look at this example here. Most adults would erase all their personal information online if they could. A GFI software surveys 600 randomly selected adults, and they show 59% of them would erase all their personal information. State the null and the alternative hypothesis. So this one says at most, okay, all of, right? Adults showed 50% would of them would erase all their information. So we use 0.5. I just have that note on there, and then I was like, but this one doesn't even use that. So then I was like confusing myself for a second. I think I have the answer right here, but most adults, if I have the word most adults, when I go to do my null, what I'm going to do is I'm going to set it up as HO, right? Like for the null. And then I do 2 dots. And then I use the symbol for what this problem is talking about. Do we have percents? Or in this problem, do we have a mean? We have a percent, okay? And this comes from our sample. So we have to be careful. That comes from our sample. So most adults would erase all their information. So I will show most adults. So I'm going to show P equals the 0.5 for most adults. Okay. If you're bigger than half, it's going to be most. So HA dot dot, right? And then we still use a P. Now, is it going to be equal, not equal, greater than, or less than when it says most adults would erase theirs, right? Then it would have to be greater than 0.5. Okay, so our null is equal to most adults, 0.5 half, and our alternative would be greater than half. Now, where did the 0.59 come in? Well, we're going to use that information to see if we have enough evidence to fail to reject the null. So if we fail to reject the null, we keep it. If we reject the null, then we go to this and we would have evidence. So we would have to do more work, and that's what 8.2 and 8.3 will show. Okay. We'll try to make this clearer than mud as we do more. So fewer than 95% of adults have cell phones. In a, I don't know what a Marist poll is, 1,500 or 1,159 adults, 87 said they have a cell phone. State the null and the alternative hypothesis. So fewer than 95% of all adults have a cell phone. So that's our claim, right? This is like the claim. And so when I go to set this up, I'm just looking at what are we testing? What is the claim amount? The claim amount is 95%. So we're going to do P is equal. Why did we use P? because it's still a percent or a proportion. Okay. And we do equal because our null is always equal. And then our hypothesis will be either not equal, greater than or equal to. So this says fewer. Well, fewer would be less than 95. So we would then, we're kind of right now ignoring the 1,159 and the 87%, because again, that's about the sample. And we would use that to decide if we take the null or the alternative. Okay. The mean pulse rate of adults is equal to 69 BPMs. For the random sample of this many, their pulse rate was this, and the standard deviation of this. So when we do a mean instead of a proportion or a percent, right? We have to have the standard deviation because that's part of our formula, which we aren't doing yet, but we're getting there. So for this, again, we're still setting it up, but what is the symbol that we use for the population's mean? Well, it kind of looks like that weird U, right? So you're up and down like that. That's the symbol we use when we're talking means. And so this is a mean pulse rate of adults is equal to, that's our claim, is equal to 69. Well, so that, oops, this should be an O, not an A. That is our claim. So that's what we're going to use on our hypothesis testing, setting up piece. And our alternative would be not equal, because it doesn't say less than, greater, less than, fewer, more. None of those words are in there. It just says the mean pulse rate of adults is 69. So it could be below, it could be above. So we state that one with the not equal. So I feel like not equal shows up when you have less information. Okay. All right, so these are 3 examples that I came up with that are all very different, and it shows all the different ways, right? We could have greater, we could have less, we could have not equal. And notice my null is always equal. It doesn't matter if it goes with the claim or not. So let's think about this. Actually, most adults, this goes with the claim here, right? Most adults. Fewer, this is the claim here. And then here, this one's the claim. So it doesn't really matter which one goes with your claim. We set it up a specific way and we either go with the claim or we don't. So 90% of your homework is just setting these up because I need you to figure out, separate the sample data, look at the claim, set up your hypothesis. Okay. We talk about some other pieces in 8.1 a little bit, but we're really going to focus on these in 8.2. A significant level, how accurate do you want to be? We did this in confidence intervals, 95, 99, how accurate? So we have that piece as well, and it plays a huge role in whether you accept something or not, right? You could be like, I'm trying to prove that people do just as well in online statistic as they do in person. I've actually done this. And so I get all this data from all my classes I've been teaching for 5 years, and I do a test. How accurate do I want to be? Well, probably 95 is good, right? What if I want to be super accurate? Well, then I can do 99. So that significant level that goes with 99 would be 0.01. Okay, so you can kind of see that written here. Okay, so that level we look at that follows 99 is like what's left, that 1%, that 5%. Okay. And we write the significant level with this weird looking, that one makes it not look, it looks a little more like a fish. That this font doesn't quite do it very much justice. And it will help us decide whether we reject or accept the null. Okay. So we'll get there in the next section. So these are the formulas for our test statistic. I just kept them in this note packet. We'll do them in the next sections, but you have them. One thing to note here is we have a requirement that the number of samples times your percent has to be bigger than 5. So if I'm testing a claim of 0.01%, like think about a drug. I don't really want people to die, right? So I want less than 1% of people to have died taking this medication. Something like that. I would have to have a huge sample, the N, to times it together to get something bigger than 5. So you can't test a claim of 1% with 2 people. It's just not going to work. Okay, that is what this is trying to tell you here. For the means, we're going to talk about a known standard deviation and a not unknown known standard deviation. This right here is very rare. Rare. Think about this. I'm collecting data. How often do you have the population standard deviation? Never. Like, if I had information about the full population, I wouldn't need a sample. Okay, so some of your homework is a little tricky because it does give you this standard deviation. Remember that standard deviation of the full population. The other symbol, the S symbol, is of the sample. So we'll have to remember those differences. So maybe we'll write that over here just to remember. This is standard deviation of the population. And the S is the standard deviation of the sample. Just so you have that. So you know what these are meaning in here and stuff. Okay, so big deal is this part. We're going to use a T in StatCrunch if we have a mean, because we'll rarely use a Z because we don't usually have the standard deviation. Okay, we will use the proportion section in StatCrunch for all of our proportions. It is using a Z, but we have an actual separate proportion section, but it is using a Z. It is the programming for the way you put in your data. That's why it has a separate section for that. Okay, this is the one that is for a standard deviation. Okay, and variance, like remember, variance is just standard deviation squared. And this one's a little bit different. We call it a chi-squared test, and we probably won't get to that. If we do, yay. If we don't, it's okay. It's just another formula. You do exactly the same way. There is a section for it in StatCrunch as well. Okay, then the two-tailed test, left-tailed, right-tailed, we talked about this, right? A left-tailed is the little tip at the bottom, low, and it goes with less than. Greater than goes with right-tailed, and it's up on top. P-value is actually newer, and I love it. It just makes hypothesis testing to me a lot easier. So we have something called the critical value method. So we find this null, we find this alternative, and this section right here, we're going to find what's called a critical value. This is the number you're at here. Right? So it's going to be a Z or a T, depending on if it's a mean or a proportion. And so we find that value, and then we find this test statistic with this formulas up here. Okay. And then we decide if that test statistic is in our rejection region. That is called the critical value method. It is the method that I learned, and I would be looking at tables. And this is the method some teachers teach. But we're really leaning towards the probability method. That's what p-value is. It is a probability of being in this section. It is easier. So we put our data in StatCrunch, and we're going to have a p-value. And if that p-value is low, so lower than that 0.01 or 0.05 on your significant level, then you're in that rejection region, or higher, depending. Okay. Well, it's not higher. It would still be the probability of being in there, so it's still lower. Anyway, so the probability of being in this section, this section, or this section. So if the P is low, the null must go. Okay. And then I have that right here. So if the P is low, the null must go. So just remember that. P is low, the null must go. So we would say we reject the null because the null must go away. And we're now going to accept or say we have evidence in favor of your alternative hypothesis. So you're either going with the null or the alternative, right? So if the P is low, you're going with the alternative. If the P is above that 0.01 or that 0.05, whatever significant level you're at. If it's above it, then you fail to reject the null and you accept it. And I don't know where your claim will be. We don't care. We'll look at that after and go with that. Okay. So this notes, we'll talk about all that different stuff. One other idea is the type error. What type of errors do we have? So our first type of error is we could make a mistake of rejecting the null when it's actually false. So we're going to make a mistake of rejecting the null. I wrote it. I was like, wait, I'm sorry. Yeah. I was reading this one after reading this one, and then I was like, wait, that's not right. The mistake of rejecting the null when it's actually true. I was like, we can't reject the null and then it's not true. Like that's the same. Anyway, okay. Say it again, Charity. The mistake of rejecting the null when it's really true. So I'm like, nope, that null is gone. I'm going to go with this alternative. This is it. I have evidence, but really this was right and you were wrong. So we had a mistake of rejecting the null when it is truly true. Okay, and then the next one, type 2 error, would be the mistake of failing to reject the null when it's really false. So I'm like, I'm failing to reject it. So I'm like, the null is true. I have evidence in favor of this when really it was the alternative. Okay, so you're allowed notes on all tests. So you can do yourself a little, cheat like I wrote here to help you with that. So you'll have to write out a couple multiple choice for what type of error you have. Okay, so I am going to, what else did I did a little chart in here, which we might refer to when we get to 8.2, but it's in the 8.1 notes. And then the examples would be more of just writing out our null and alternative. So we're not doing this full test. So 8.1 had so much stuff in it that I narrowed it down. I still kept the notes having some of the stuff, but really, I want you to start to understand that we're setting up a null hypothesis, an alternative, and we're going towards finding the probability of being in that rejection region. And if we reject the null, we're saying the alternative is true-ish, right? Not proof, but we have evidence in favor. If we fail to reject the null, then we're going with the null, that it's equal to whatever value. I actually think we're good. I don't know if I want to cover, or maybe I'll just do problem 1 real quick. So a friend is tested to see whether he can tell bottled water from tap water. There are 90 trials, half with bottled water and half with tap water. He gets 54 right. What is the null hypothesis? So he's testing to see if he can tell bottled water from tap water. So see how it says like he got 54 out of 90? Is that a mean or is that a proportion? It's a proportion because I got so many out of so many, or if I have a percent, that's proportion. So when I go to set up this, I know I want this and this, dot, 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 dot. I know I want a P. I want a P because it's a proportion. That's important. You'll get it wrong if you don't put P. And then this is always equal. Okay, so we're either, we can see if he can tell. So we want to see if he can tell at least half of them. It doesn't give a specific value. So it just says, we want to see if he can tell the difference between them. 90 trials. So we don't know anything else. So we would say not equal. So we don't use the 54 out of 90. That is our sample. We use that to prove which one is right. Okay, oops, this is the answer to this part. Okay, I think I'm just going to stop there. I think you're good. All right, I'm going to stop there on my video. Lots of null and alternative. Let me know if you need help.